Good evening and welcome. I am Rada Mihalcea. I'm a professor of computer science here at Michigan. I'm also the director of the Artificial Intelligence Laboratory, and I work in natural language processing.
My name is Laura Wendlandt. I am a PhD student here at the University of Michigan, and I also work in natural language processing with Rada.
And my name is Helen Haas, and I'm a Master of Music student in voice at Michigan's School of Music, Theater, and Dance.
We are thrilled to have you join us on this evening. It is a unique evening for us, and we hope it will be a unique evening for you. Aside from the fact that this is probably the very first time for many, if not all of you, that you will get to listen to an opera performance and computer science talks during the same event. This evening is unique because it celebrates the amazing contributions that women have made in the field of computer science since the very beginnings of the field.
In fact, the very first computer programmer was a woman, and her name was Ada Lovelace. She was born in 1815 in London, which is the same year that Napoleon was finally defeated at the Battle of Waterloo. So this was a long time before modern computers were built, but already mathematicians were starting to imagine calculating machines that could automatically solve equations. And we're really excited to share the story of her remarkable life with you tonight.
Ada Lovelace was a key contributor and publisher of fellow mathematician Charles Babbage's Analytical Engine, a mechanical general-purpose computer. The annotations that she wrote within this publication were very useful in the early history of computers. In particular, Ada Lovelace had a vision for a computer's potential to do more than just calculate numbers. Later, students from the School of Music, Theater, and Dance will perform a short opera that dramatizes Ada's life and conflicts of work and family in a time when careers in mathematics were all but non-existent for women.
Fast forward 175 years, we are now witnessing the most exciting time in computer science. The field is truly booming. We now have the largest ever number of students in computer science departments. We have a growing number of classes being offered to elementary schools, middle schools, and high schools. There is a very large number of computer science companies that are working on solutions to critical problems. Today, computer science is pervasive in everything we do, from education to medicine to transportation to well-being. And women have been core contributors to this revolution.
Tonight, we're going to start with the present, and you're going to hear 8 computer science talks from women who are leading researchers at Michigan who are doing awesome computer science research in a number of fields. Healthcare, social science, space exploration, education, human interaction. And as we hear about their research, you'll hear about where computer science is going in the future.
As we will introduce our speakers, we will also share with you a few interesting info bits about Ada Lovelace's life. The speakers will be introduced by the people who volunteered their time to make this event possible. We want to express our deepest thanks to them, to Alison McDonald, who organized publicity and registration. She also arranged the reception after this event, along with Mei-Xing Dong and Veronica Perez-Rosas. To Zoe Black and Anna Kuza, who designed the programs for the event, and Zoe also designed the posters. To Aishwarya Reganti, who researched the life of Ada Lovelace. To Rita Mehta and Betsy Wall, both speaker coaches for TEDx at U of M, who help our speakers prepare for this event. Nell Doherty and Amy Klinkle, who coordinated sponsorship. We also want to thank the composer, Kamala Sankaram, for her collaboration correspondence in the performance of her work Enchantress. Helen Haas for producing the opera Enchantress, as well as all the School of Music, Theater, and Dance students who have been a part of this production both on and off stage. Our deepest appreciation goes to all the speakers who agreed to share with us some of the exciting research that they are currently doing. And of course, to all of you for joining us tonight on this celebration of women in computing.
Finally, many thanks to our very generous sponsors, the School of Music, Theater, and Dance Meta Wiser Excel Fund, the Arts Engine Micro Grant Program, the Diversity and Inclusion Office, Google, and Girls Encoded. One last quick announcement before we start our program. We'd like to point you to an ongoing exhibit here at Michigan, Hidden Figures, When the Computer Wore a Skirt, celebrating the contributions of University of Michigan women who were and are at the forefront of science, technology, engineering, and math. This exhibit is taking place in the Duderstadt Center right here on North Campus, and it will be open through November 22nd. So if you have some time, you should stop by and see this cool part of our university's history.
All right, and now let me introduce our first speaker. Jaran Budak is a professor at the School of Information, and she is interested in computational social science.
Good, I don't need this, right? Oh, yes, I do. Thank you. Okay. Hi, everyone. It's my great pleasure to be here and talk to you as part of this very fun event. I'm Jaran Budak. I'm an assistant professor at the School of Information here at University of Michigan. My background is in computer science. Both my undergraduate and my PhD were in this field, and I study computational social science problems, which means that I use computer science techniques to study social science problems, that is, problems that have social, political, or policy implications. So one subfield within computational social science is political communication, which is what I'm going to be talking about. And my goal here is to convince you that as computer scientists, we can and do work on problems that have real societal implications, and with our methods, we can help solve problems in important areas such as political communication. So what is political communication? It is the study of the dissemination, the processing, and the production of information and its effects within a political context. There are three types of agents that we study here. One type of agent is politicians, and we study how they communicate with the broader public. Second type of agent is citizens. We study how they process information that they get from politicians and how they communicate with each other to make decisions. And the third type of agent is mass media or news media, and how they play an intermediary role between the citizens and the politicians. So as computer science gets more involved in this field, as we have larger data sets and computational methods to study these problems, we can look at these questions at a scale and a detail that was never possible before. So I would like to now give two examples from my own research to try to back up that claim. The first example is going to be about the third agent I talked about, which is news media. And the question that we looked at in a recent study was to understand and quantify news media bias. So if you're trying to understand for a news outlet that you're reading news from, just how right-leaning or left-leaning they are, or the content that they produce is, how would you go about doing that? Right? So how would you go about placing a news organization such as New York Times, Fox News, CNN, whatever comes to your mind, in this one-dimensional space? This is a rather hard problem. It requires you to make sense of a lot of news articles. And here we use computer science techniques such as supervised classification and crowdsourcing to tackle this problem. And we were able to identify for commonly read news outlets in the US one number that tells you just how right or left-leaning they are. And to give you an idea of just how computer science methods and studies can have real-world impact, the estimation that we came up with was picked up by various outlets, including Huffington Post, who came up with a tool to help guide their readers to news outlets according to just how much they care about perhaps trustworthiness, and on the one dimension, the bias or the ideological position that we estimated here at University of Michigan. The second study that I will talk about is going to be about the second agent I mentioned, which is the citizens. And the study is about Turkey, which is, by the way, where I'm from. And the study is about a protest movement that happened in Turkey in 2013. It was the biggest in the Turkish modern history, and it was a movement that was against the government that brought together people from various walks of life, various different backgrounds and ideological leanings. It brought people from far left and far right together in one movement. The characteristic, one of the defining characteristics of this movement was solidarity. To an extent that the symbol of the movement, at least one of the symbols of the movement, was a whirling dervish in a gas mask, the gas mask referring to the police brutality that the activists faced, and the whirling dervish referring to the openness of the movement and the solidarity that came with it. So the question is, how can a movement bring together people from far left and far right in one movement? It sounds pretty bizarre, what happens to that solidarity when the movement dissolves? And we used social media data and statistical methods to basically track and understand people's behavior towards each other and observe how they were before the movement, during the movement, after the movement to answer this question. So I hope that I was able to convince you to at least some extent just how much computer scientists can play a role in society and how much we can have fun doing that. So thank you.
Hello. Before our next speaker, we have a little fun fact for you about the life of Ada Lovelace. She, when she was 12 years old, decided that she wanted to learn how to fly. So she put a lot of time into this problem, like an engineer would. She studied birds, she gathered feather, silk, paper, and she ended up writing a guide on how to fly called, anyone got a guess? It's called Flyology, study of flying. My name is Rita Mehta. I'm an undergraduate senior in computer science, and I helped with the speaker coaching for this event. And I'm here to introduce a great speaker who is a professor in computer science and engineering, and who will be speaking about computer architecture, which she researches. So everyone, please welcome warmly Rituparna Das.
Hello, everyone. So I work in making the hardware, computer hardware, incredibly fast. So I like to push the frontiers of processor design. And so what comes to your mind when you think of a computer? Well, I'll tell you a few things which come to my mind, and I hope these resonate with you too. So today, computers are incredibly fast. They're very high performance. They scale to very large systems, which are warehouse scale, to very miniaturized systems which are collecting and sensing data all over the world. And they can do that at very good speed, and also at also they consume a lot of power and energy. So one of the problems which we focus on is how to make them low power and very energy efficient. A small fact there is when you do a Google search, can you imagine how much energy you burn? Well, if you want to boil a cup of water, that's how much energy you burn for a very simple Google search. So yeah, that problem is there, and we try to optimize that too. So given these performance constraints and energy optimizations, so where are we today? Well, today if you open up your computer and look at the hardware inside it, each processor, the very little tiny chip, has got billions of transistors on them. Few years back, we were at 3 billion processors. This is out of your Mac. If you open up an old Mac, you get this chip processor out of it. We have moved to 5 billion transistors with accelerators, right? And it's a march, it's a joy ride which has kept going forward, giving us incredible speed and performance. This was back in 2014, I believe, when my daughter was born, I think. It was 10 billion transistors. And today, when you want to run your artificial intelligence algorithms, it's 10 billion transistors on these GPU accelerators, which make all this happen. So I believe that good hardware is key to make all computer systems work and solve all these societal problems which we are working on. Well, that was all good news. But what's happening now is, some of you might have heard to it, but the joyride is kind of coming to an end, some say. Well, Intel still says it doesn't, but well, you know, they are making billions of dollars, so. But I'm an academic, right? So I have to tell the truth. And so this is what is happening. It's flattening out. The chips were shrinking. We're putting more and more transistors. So transistor per dollar was actually going down. But now what we see is it's a flattening curve. So we are at that inflection point. So this is bad news for the world. For me, it's a very good news. Why? Because I can be very creative now. Now we have to come up with very good solutions to kind of push the frontier even further in spite of the technology diminishing returns from the technology. So what can we do? What are some of the interesting things we are looking at? Well, I'll talk about 3 things today. One of it is kind of speculative, but I think it's also happening. So first thing which processor designers are doing is they're trying to customize computing. So what they're doing is they're trying to build processors and hardware which is very tuned to your applications. And therefore, they can give you a lot of performance at very less energy cost. So a few examples of that. So this is the Tensor processing unit which Google came out with, and maybe a year or so back. And this makes AI, artificial intelligence algorithms, run very fast. And you can do training of these models and inferences on these sort of accelerators. That's what the terminology here is. Another example is, and so this is a software giant which is trying to build this hardware. So we want to kind of extract that. And another example is the Microsoft's Bing. So how many of you use Bing here? Anybody? Ouch. I mean, that's why they're building this. So, well, I don't think they've convinced me. I still use Google. But, well, they're building hardware so that they can make Bing search very fast and provide you good results, right? So those are some of the trends where they are building customized hardware. What I'm with my group doing at Michigan, one of the things, well, I care a lot about the health. And one of the problems which is very exciting to me and our group together and my collaborators is how do we make precision health happen? So we are looking at custom processor for genomics. So every human being is different, and we have to build fast processors for that. Another topic here which we are looking at is compute memory. Well, today processors are taking incredibly a lot of time to fetch data from memory. What if we blur the line between compute and memory so much that you transform memory into compute? So here is a simple picture which shows how much of area and energy is going between compute and memory today. And if you put in more compute here, it's shrinking. But what we want to do is we want to take the passive memory and turn that into lots and lots of compute power, and thereby shrink that pie and improve our performance a lot. We can build new memory technologies like memristors, which can, again, transform computing. I'll leave you with a parting thought. Maybe the next thing is also quantum computing, and it is no longer a science fiction. There's actually a startup which is doing it. So maybe that's the new answer, post-silicon. Thank you.
Okay, so following up with Ada Lovelace's life, after studying the anatomy of birds and the suitability of different materials, young Ada made a plan to build a winged flying apparatus before moving on to powered flying. I have made a scheme, Ada wrote to her mother, to make a thing in the form of, I wonder if anyone can guess, in the form of a horse. with a steam engine on the inside, so contrived, so an immense pair of wings can be moved by it. So the horse can be carried up into the air while having a person sitting on it. My name is Anna Kuza. I'm an undergraduate here, majoring in CS and math. And today I'm going to introduce you to another undergraduate who is studying computer science and engineering, working in the machine and crowds lab at UM. Well, let's give a round of applause to Isabel Wong.
So imagine you're in high school and you're taking a class on game development. And for your latest project, you decide to work with 3 or 4 of your closest friends on a Super Mario type of game. So how is this design process going to work? How can all of you best consider all your design choices against each other and weigh the cost benefits of what you're working on all together on one platform? So the best way for us to visualize what we're working on is by building a prototype for our game. And the most straightforward way for us to do this is just to write code. The problem is that this takes way too long, requires us to accumulate resources that we may not immediately have access to, and also just requires us to put in a lot of effort that probably won't pay off in the end because our ideas are continuously changing. So how about we look at primitive tools like pen and paper? So as you can tell, I'm not a very good artist, and using paper really limits the scope and dimensionality of what we're working on. And considering the amount of detail that we want to include in our prototype, this task may prove to be really tedious and take a lot of time. So how can we speed this process up? How about we work with our friends that we're working with on the same project and all collaborate on the same session? But the problem is that I'm using one piece of paper and one pen. So how can we best accumulate all of our ideas together in one session? If my friends want to actively contribute, they're going to have to either work in their own session on a separate piece of paper, or they'll have to physically reach over me in an uncomfortable manner so that we can all work in the same session. So this is pretty implausible. So now let's try another method. So now let's look at a tool like Google Draw. So now we're all working on separate laptops and in the same synced session. And you would think that this is very conducive to group collaboration, but it's not, even though we have synced sessions for that purpose. So if you refer to this example, I could be trying to add bricks to our synced session, and my friend is trying to contribute, and let's say my friend tries to add a background. But then this overlays the work that I was previously working on. So then now, in my confusion, we're both trying to fix the mistakes that both of us made, and then we just end up overwriting each other's work again and again. So this is a problem, and this happens because we can't consider all of our design choices together on one platform and work together without accidental conflict. And we also can't mock up our prototype fast enough to consider all of our design choices against each other. And the quality of our work is not good enough, and Google Draw really limits our actions because of the provided functionalities that it has, which restricts us to producing static images on the screen. So in the end, we end up spending way too much time on a changing prototype, and the quality of our work is not reflective of the amount of time and effort that we're putting into it. So now let's look at a tool like Apparition, which is something that I've been working on for the past 2 years. So how can we make use of the crowd, which consists of many paid workers who do small tasks via systems like Amazon Mechanical Turk to do this job for us? So now my group and I can discuss our work in real time. And as we're talking, our ideas are magically being created on the screen right in front of us. But in reality, these crowd workers are actually listening to what we're saying, and they're iterating what we're talking about on the screen. So edits are being made to reflect these changes that we're talking about in real time, and the quality of our work is being improved on second by second. So for example, within a few seconds, a simple triangle on our screen can become a full-fledged Super Mario Goomba. So now my friends and I were discussing our Super Mario World design, and our prototype is just showing up in front of us in real time. We can easily make a mistake and then backtrack and move it in another direction, but our prototype will still reflect these changes that we're talking about. And then none of us had to lift a finger or even wait for maybe a few hours to see a full iteration of our prototype, but now we can just see it within the amount of time that we take to discuss our ideas. And then now, because of the shortened time span, we can work on several iterations of our prototype within a reasonable amount of time. So now I've discussed the impact of a tool like this in the user space, but what else can a tool like this contribute? So don't you think it'd be great if we could teach computers to do this work for us? Why are we paying people to do this work if we could just automate this entire process? So actually, this is a problem that's very, very difficult to solve. We want machines to be able to learn the input that we give it, but in this case, the input is natural language, which is very, very complex. So how can we take natural language and translate this to complicated behaviors, such as animations or cause and effect actions between different characters? So a tool like this will actually provide the data that we need in order to teach machines such behaviors. And the problem is that right now, real people can understand what real people are talking about way better than machines can. So in the future, we hope that computers will be able to learn these behaviors in an efficient manner. So apparition is effective for users in the user space, but it also provides a foundation for ventures in machine learning and natural language processing in the future. Thank you.
At the age of 17, Ada Lovelace met the inventor and the mathematician Charles Babbage, and she watched him demonstrate a model portion of his difference engine. This difference engine was a massive, massive mathematical calculating machine, and this difference engine, is what gave him the name, the father of the computer. While working with Babbage, Lovelace wrote a paper describing how this machine could be programmed by code to calculate Bernoulli numbers. Some call this the first algorithm carried out by a machine, and therefore the first computer program. My name is Betsy Wall, and I am a senior in biomolecular science, and I participated by helping with speaker coaching for this event. It is my pleasure to introduce to you the next speaker. She is a professor in computer science and engineering, and she is conducting research in machine learning and healthcare. Please welcome Jenna Weens.
All right, so before Jon Snow was King of the North, he was a physician in London during the 1800s, around the same time as a major cholera outbreak. Cholera is an infectious disease that spread through the Soho district of London in 1854, killing 500 people in just 1 week. At the time, people believed that the disease was spread through bad air. But Jon Snow believed otherwise. He believed that the disease was spread through contaminated water. To prove his theory, he set out to collect data. He plotted on a map of the district all of the cases of cholera in red and the water pumps throughout the district in blue. By clustering the data, Jon Snow was able to show that the vast majority of cholera cases could be attributed to the Broad Street pump. Armed with these data, he convinced officials to decommission the pump, saving hundreds, if not thousands, of lives. In some sense, Jon Snow was a data scientist. Today's data scientists use machine learning to automatically detect patterns in data. These patterns can then be used to make predictions about the future. For example, which districts are going to have a cholera outbreak in the future, or increase our understanding about the current world. In contrast to the techniques that Jon Snow was using, machine learning techniques can take advantage of the large amounts of data that we're collecting today. For example, in healthcare, we're collecting an immense amount of patient data. Everything from what medications a patient's on to genetic information. And while clinicians are spending ever more time studying data about their patients, they're still ignoring the vast majority of it. So my research focuses on using machine learning and developing machine learning techniques to automatically identify patterns in the data associated with disease. Then we can identify patients who are at greatest risk for a particular bad outcome. One outcome that we focused a considerable amount of effort on is predicting infections with Clostridium difficile. C. diff is a bacteria that takes over the gut when normal or healthy bacteria get wiped out. It can lead to colitis and even death, and is associated with excess medical costs of over $1 billion per year in the US. We hypothesize that one of the reasons why this disease remains so stubbornly prevalent in hospitals today is because we lack an effective tool for measuring patient risk. The risk of infection is multifactorial. There are many different risk factors. But we know that a patient needs to be both susceptible and exposed to get the infection. Now, susceptibility is a proxy for how sick the patient is, whereas exposure is typically measured as a function of the infection status of one's neighbors. But a recent study came out showing that roughly 50% of infections at a hospital were genetically distinct from all other known infections at that hospital. So the question becomes, who is spreading the disease? Who is the culprit? We believe that it might be hidden carriers. Patients in the hospital with no signs or symptoms of C. diff, but are still contributing to the spread of disease. To try to identify these hidden carriers, we developed techniques that represent the hospital as a network, where the nodes correspond to patients and the edges connecting nodes correspond to proximity. So two patients would be connected if they, for example, shared a room or shared a healthcare worker. Now, using these techniques, we can take a data set of patients, identify who's connected to whom, identify who has an infection with C. diff, and then estimate who's most likely spreading the disease. Like Jon Snow, we can identify the source and then take action to reduce the spread of infection. Thank you.
At least one geek stereotype was true of Ada. She was a terrible dresser. A disapproving housekeeper described her to a visitor as not so well dressed as her maid. She was also a bit socially awkward. After what must have been a pretty boring conversation on math, one woman declared, Babbage, not Byron, should have been her father. I'm delighted to introduce the next speaker. Aparna Garimella is a PhD student in computer science, where she does research on natural language processing. Please join me in welcoming Aparna.
Today I'll talk about demographic-aware natural language processing. So I'll introduce you to my area of research, natural language processing, and then I'll emphasize the importance of demographics in dealing with language, and hopefully motivate you, some of you, to pursue NLP in the future. So what is natural language? It is the language that people naturally use to interact with each other. Could be English, Spanish, so on. So as opposed to a programming language, it doesn't have any fixed format. If we spoke a different language, we would perceive a somewhat different world. Hence, understanding language brings us one step closer to understanding the way people perceive the external world. And natural language processing does exactly this. It uses computational techniques, computers, to understand or generate natural language. For example, the Google Translate or Google Search, given some text to it, it understands and generates some response to us. So what are demographics in language? They are the background features of people using certain language. They could include gender, industry, location, etc. Males, females are two demographic groups, so on. So here I'll present a result of one interesting study by a social linguist, Lera Boroditsky. She wanted to see how different people perceive outside world and how much their language affects such perceptions. So she gave people a list of words and asked them to describe those words. For the word bridge, Spanish speakers said bridges are big, dangerous, sturdy, etc., whereas German speakers said bridges are elegant, beautiful, fragile, so on. So it so happens that the Spanish word for bridge is masculine, while the German word is feminine. So the fact that their native languages had gender for this word affected the way they perceived that word. In other words, their language can affect the thought. So inspired by such studies, we wanted to see if demographics of people can also affect their thought process. Here is again another result of our study, the word decision. Indians describe decisions in terms of business, finance, marketing, while Americans, they described it in terms of playing games, winning teams, etc. Yeah, so demographics also affect the thought process. It's pretty obvious. And my research includes, can we use such demographic information of people to do certain language tasks better? So we look at a task, NLP task, word associations. Given a word, it predicts the first word that you think of. For example, for the word car, you could think of gas, drive, so on. Or probably I would think of music, because the first thing I do when I enter a car is start the radio. So it's the first word that you think of based on your experiences. And again, these associations vary with demographics. The word sleep, younger group associated it with dream, elder group with being awake. Yes. So in other words, we want the association prediction system to take into account the demographics of people. But unfortunately, the existing models for association prediction do not take them into account. They use this one-size-fits-all approach, have one response for sleep, irrespective of the person being young or old, Indian, American, so on. But in our work, what we try to do is have this better NLP model to predict associations by accounting for demographics, have different responses for Americans, Indians, young people, elder people, so on. We look at gender and location, males and females from India and United States. Here are some interesting examples to illustrate such differences that they do indeed exist. The word expect, males expect nothing in majority, whereas females a baby. Admit, Indians admit people to hospital, whereas Americans, they admit their guilt, their crime. Maybe the law system is stricter in the United States. Our model outperforms this one-size-fits approach, so that's exactly what we wanted to achieve. Including demographics can improve certain NLP tasks. So I would like to conclude saying language is not necessarily the interaction between words as we all think of. It's much more than that. It's the interaction between people using that language. So to understand language better, I guess one should start looking at the demographics of people, their personalities, etc., so that we can do things better. And if you're interested in more in this area of research, I guess you can look up our group website or my advisor's website. Thank you.
Following up with Ada Lovelace facts, Ada Lovelace had already foreseen that computers can be used for multi-purpose functionalities, although Charles Babbage always thought that computers are just used for complex calculations. She had already mused that data, such as images, text, sound, or even music, can be converted into digital formats and modified by computer systems, things that we call today as natural language processing or image processing. I am Aishwarya Andreganti. I am an undergraduate research intern at the Computer Science Department, and I take pleasure in welcoming the next speaker of today's evening, who's Valeria Bertacco, and she works on sustainable hardware development.
Good evening, everybody, and thank you very much for joining this event. Tonight, I want to tell you a story. Once upon a time, computers looked all the same. You got a keyboard, you got a monitor, and you got to do boring work or homework. But today, computers are a lot of fun. They come in all sorts of shapes and colors, and they can track your heartbeat. They can cut your belly open. They can prepare the temperature at the right level in your house when you go home, drive your car, even fly around and spy on your neighbors. But what's inside? Inside these computers are microchips, little plastic box like this, pretty small, and they're chock full of transistors. You know what's a transistor? It has a function of a light switch, and they work like minions. You cannot do much with one, but you get a lot of them, you can get pretty cool work. And there are a lot of transistors inside these microchips. How many? Well, in the 70s it was about 1,000. In the 90s it was about 1 million. Nowadays it's billions. Pretty much we can put as many transistors in one of these little boxes as there are stars in the Milky Way. So these are some of the chips that people make today, and there are 10 or 20 billion transistors all inside one little box. Now, how do you put more and more things inside the same box? You make it small. And smaller, and smaller, and smaller. And indeed, they had a name for that. They call it Moore's Law. And they basically said, you know what? Give me a year and a half, I'll pack twice as many in the same box. And that worked for a while. And then it didn't work anymore. And they said, well, give me 3 years. I'll pack twice as many in the same box. And that's where we are today. But it's not working anymore. We cannot really pack much more anymore. And they're getting so fragile and so difficult to make. Transistors today are so small that you can put 10,000 of them to make the size of a human body cell. Then we have trillions of cells in the body. So this is how small they are. So what can we do about it? Well, at the same time, the smaller the transistor, the more it costs to pack them up in a box. Putting together a new design today costs something like $120, $150 million. How many people can spend $150 million because they have a new idea? Very few. And the fewer people can play the game, the less innovation is in the industry. Just to give you a sense of the contrast, think about the software industry. You see the little yellow sliver on top of the 120 million line? Teeny, teeny, teeny? That $500,000, and that was enough to make Instagram and put it in the market. In software, lots of people can play the game. It doesn't cost a lot of money. You have an idea, you can make it happen. So what can we do? This is where we are today. The technology innovation was fueled by making smaller transistors and managing the cost. And both those fuel tanks are falling out. And that's killing the innovation. And to address that, I'm part of a team of researchers, a new team of researchers, called Ada, coincidentally, who wants to refuel innovation in computer design by thinking about doing different types of transistors, which are not any smaller, but they're different. Maybe they can do better stuff. And they can think about what do people need in software so we can
tune in for exactly what we need and give you better computation and better performance. So the center tries to leverage new type of computing little switches and minions and leverage what are the demands of the application that people have and people will have in the near future. I mean, the software innovation is skyrocketing. There are always new needs. And what do they want to do? They want to give you new, colorful, of all sorts of different shapes computers so that there can be a lot of innovation. And then one of the key things in the middle of all this effort is to boost innovation by lowering the cost. The lower the cost of new computers, the more people can play the game. And just as an example, one of the ways we are trying to lower the cost of designing system is by thinking about hardware design as a way where I give you a few different types of building blocks in the base, and you can put together the building blocks in many different ways, like Legos. And so every time you have a new idea, you can quickly do a new computer system. Similarly to how you can develop a new automated loom that fascinated so much Ada Lovelace. Thank you.
One of the most incredible things about Ada Lovelace is that her ideas were nearly a century ahead of when they were appreciated. So she first published a paper on the analytical engine in 1843, and it didn't gain a very wide following. But it was republished in 1954 at the dawn of the computer era, and it instantly gained a much larger following, and her ideas began to be recognized as groundbreaking in computing. And to continue in our series of Women in Computing, I'd like to introduce our next speaker, Nejmia Oze, who is a professor in electrical engineering and computer science, where she researches cyber-physical systems. Please welcome her.
You probably all heard about self-driving cars. We have them in Ann Arbor, delivering pizza. We will have an autonomous shuttle in North Campus. How do you feel about them? Are you excited? Or do they make you nervous? How do we know they are safe? Here in University of Michigan, we are working on new technologies to make self-driving cars safe. Have you heard about MCD? MCD is our test track where we develop, test, and evaluate new technologies for vehicles and mobility, and to make sure they are safe. You might ask, what does a self-driving car to do with computer science? Currently, in a self-driving car, we have almost 100 small and large computers. These computers are running specialized algorithms. An algorithm is a set of instructions that tells a computer what to do. And in a self-driving car, these algorithms consist of hundreds of millions of lines of code. I work on cyber-physical systems. Self-driving cars are just an example of cyber-physical systems. Cyber-physical systems have a cyber part consisting of computers and a physical part governed by the rules of physics, like the motion of a robot or electricity in a smart home. Computers collect data from the physical world through sensors. They process this data and make decisions. Then they control the behavior of the physical world through actuators. This sensing, decision-making, and acting loop is called a feedback loop. and I researched how to design and understand these feedback loops. But there's a challenge in designing these loops. We need to guarantee safety, reliability, and efficiency when your code is no more confined in your laptop or desktop, but it rather interacts with the physical world. And to address this challenge, we are using tools from several different disciplines. We are using tools from computer science, electrical engineering, logic, math, and other engineering disciplines. I do like writing code, and I code a lot in my research. But imagine reliably writing hundreds of millions of lines of code required for a self-driving car. Can we really write that much code? That's where my research comes into play. I work on controller synthesis. I am trying to develop higher level algorithms that can generate these algorithms that will run on physical systems and that will make these physical systems behave. Here are the ingredients of controller synthesis. We develop mathematical models of the physical world that tells the computer what the physical system is capable of. We also develop mathematical models for constraints and objectives that tells the computer what is the task in hand. Then our algorithms figure out how to accomplish this task and generate the required code to accomplish this task. This is kind of a brain implant for your autonomous system. So we just tell the computer what we want to do, and it generates the code for us. How does it work in real life? So here are our algorithms in action in MCD. This is an the video is not playing, but this is an autonomous vehicle driven by an algorithm. And that algorithm is not designed by a human, it's rather designed by a computer. Hear me with Robonaut at Johnson Space Center. We are designing algorithms for Robonaut so that it can safely interact with the astronauts in the International Space Station. We are also designing algorithms for Robonaut to make it more aware of its own health so that it won't need maintenance so much. To summarize, we are developing new science and technology to enable safe autonomy. And more importantly, we are having fun doing so.
In the 1970s, the US Department of Defense developed a new programming language to replace the hundreds that it was previously using in the military. When US Navy Commander Jack Cooper suggested naming the language Ada, everyone agreed. Ada is still used today in real-time systems in airline, financial, space, transportation, financial, and infrastructure industries. My name is Zoe Black. I am an undergraduate senior studying art and design. I designed the poster and the brochures today, and it is my pleasure to introduce the next speaker. So Emily Mower-Provost is a professor in computer science and engineering, where she researches computational models of emotion.
Hi everyone, I am so excited today to talk to you about our work in human-centered computing, trying to understand how we could use speech and other signals to understand behavior. But before I do that, I want to provide a little background on how I started in this field. Because it's amazing when you see people talking about the research that they do, but it's never really clear how they got there. And so I'm going to just go back and do a little bit of history. So first, I'm going to take you back to circa 2004. I was super excited to be starting grad school because it meant I was going to change the world. Except I had no idea how. So I got to USC and I started watching videos. I watched a lot of videos of robots interacting with people after they'd had a stroke and they were recovering. And I was struck by the fact that time and time again, the robot understood exactly what someone was doing, but didn't at all understand how they were when they were doing it. And so I thought to myself, well, what's missing? What's missing is emotion. And so what I wanted to do was understand how we could understand the human perception process so that we'd be able to design technologies that could really use this information. And so I started simple. Always start simple. And so I designed these really simple animated interfaces, and they were designed to sort of tease apart the effects of audio and video. So they'd have one emotion on the face, another emotion on the voice. That way you could begin to understand how people were integrating these things that didn't really match. But clearly that's not what people look like. At least that's not what anyone I know looks like. And so when I got to Michigan, we created some more, and I'm going to play them. I think they actually might be quite loud, so apologies in advance.
A third volume remains to be published.
Not sure it's clear, but that's generally perceived as something angry. And I was interested to find out, well, what happens when you change the information in the voice?
A third volume remains to be published.
Same video, but now the emotion on the voice is happy.
A third volume remains to be published.
Same video, now the emotion's neutral. And I was interested to find out, well, what do dynamics give us? What can we learn by looking at how emotion varies in time? Which is what we mostly focus on now. But really the takeaway is that it's not just what we say, it's how we say it.
Delayed bag. Yes. Peoria. Peoria. No. Peoria. P-I-A. No, can I talk to a person?
So it's not just that she's saying, no, can I talk to a person? It's the volume of her voice, it's how the pitch is changing. All of these things are indicating to us that she's angry. And as it turns out, this type of technology has huge influence, not only in post-stroke, but also in the design of interactive agents designed to work with us, to teach us. But increasingly, we are seeing this technology in the realm of behavioral research. We're looking at conversational cues that allow researchers to understand what differentiates the speech pattern of kids with autism and those who are typically developing. The conversation cues that allow us to understand that someone's at risk of depression, or that someone's at risk for having elevated mood episodes, perhaps mania or depression. General mental health in the case of schizophrenia. There's even work on trying to understand relationship dynamics that lead to more positive or more negative outcome. But fundamentally, what we're trying to understand are the conversation dynamics that will allow our agents to interact naturally with us. Now, when I say that, the question is, what does that mean? How do our agents actually do this? So the way it normally works is we take some kind of data that we've recorded in any number of ways, and we extract the information that we care about, in this case, speech. And our goal is to then take this information, which is varying widely in time, and associate it with some label. Perhaps we're interested in how some kind of behavior is varying over time. And this is the process that we repeat again and again and again. But this is hard. When I put labels in quotes, it's because that's not an easy process. If I see this image, what is this image to you? To me, when I look at that, I see anger, I see aggression, I see rage. But as it turns out, if I see the whole picture, that's not what that is. That's happiness, that's elation, that's pride. And so part of why this field is as challenging as it is because the very notion of truth is not clear. The type of behavior I should be looking at to understand that truth is not necessarily clear. Trying to figure out how time plays in, not necessarily clear. All of these are engineering challenges. And it matters. We've been doing work with the Depression Center for the last 5 years or so, trying to understand the conversation cues that would allow us to predict if someone's at risk of developing a manic or a depressive episode, heightened mood or lowered mood. These terms are often used in a very colloquial way, but transitioning into either mania or depression have really severe consequences for both an individual and his or her family. And we've been trying to find the check engine lights, we're near Detroit, so we have to call it that, the check engine lights that might indicate that someone's in need of care immediately. Because if we can find those using speech, then instead of allowing them to transition, we can make sure that people are on a stable course. And that has real impact. And so what I want to leave with is that not only does technology involve really having societally relevant goals, But fundamentally, engineering is about people. It's about the people that you develop technology for. It's about your teammates while you're developing technology. It's about the person that's sitting next to you that you just have conversations with. So for anyone considering going into engineering, the next time someone tells you, oh, if you do computer science, electrical engineering, you're just going to be sitting in front of a computer and never talk to anybody, remember, that's not engineering. Engineering is fundamentally people. So go computer science.
Having had a glimpse into some of the amazing research done right now by women in the field of computing, having also learned about some of Ada's early interests, it is now time to delve into a musical story of Ada's life and scientific passions.